This is the tutorial for the Parallax Lab. Parallax is one of the most important tools we can use to measure the distances to nearby stars. But the technique is really just an application of the process of triangulation used here on Earth. In this lab, you can practice measuring parallax to objects around you and see just how far away you can measure distances. Measuring parallax involves measuring angles between objects at a distance, so we'll need to make an angle measurer to do this. The lab write-up has a template for the angle measurer. You should print this out and cut out the two pieces. If you can print it out on cardstock, that works best, but you can also print it on ordinary paper and tape it to a piece of cardboard. The pointer piece needs to attach to the scale piece with a push pin, so that it can rotate around the axis. You may need to use a cork or something similar to poke the push pin into. There are arrows attached to each piece of the measurer. By lining these arrows up with objects at a distance, you can measure the angles between them. The other things you'll need for this lab are a ruler and a stable platform to set your angle measurer down on. A small table, bench, or even a railing works well for this. The idea behind parallax is that you can compare the positions of two objects to find the distance to the nearer one. We'll call the closer object the target. This should be at least 3 and as much as 20 meters away. The other object is the reference. This should be a lot further away than the target. To make your first observation, set the angle measurer on a platform and sight along it from the pushpin. Line up the reference arrow, the point sticking up from the front of the scale piece of the measurer, towards your reference object. This will give a straight line from the pushpin through the arrow to the reference object. Then hold the scale part of the angle measurer steady and move the pointer so that it lines up with your target. When you've got one arrow pointed at the reference and the other arrow pointed at the target, record the angle between them listed on the scale. After you record the angle, move the angle measurer a measured distance to the left or right, perpendicular to the line to the target. Use a ruler to carefully measure how far you've moved the angle measurer. This is the baseline, and it's a key part of your observation. The lab recommends a baseline of around 30 centimeters or 1 foot to begin with. From this new location, line up the reference and target arrows again and record the new angle they make. Note that if this angle is only a degree or two different from the first angle, you may need to use a larger baseline in order to get a sufficiently accurate measurement. If so, just double the distance you move the measurer and try again. When you've got your two angle measurements, fill them into Table 1 and subtract them to get the parallax angle, the amount the angle changes between the two observations. Again, if this change of angle is only a degree or two, you should probably try again with a larger baseline. Also, record the size of the baseline and give the units. Make a simple sketch of your setup with the target and reference objects labeled, and also take a picture of your experiment. The lab gives you two different ways of calculating distance from the information you've recorded. The first one is the full geometric calculation using trig functions. If you've ever taken geometry, you may recognize this formula as the way to measure one side of a right triangle if you know the angle and another side. Even if you haven't used this sort of trig function before, you can still do the calculation on a scientific calculator. You should check that the calculator is working in the right units for angle. Try calculating the tangent of 45. If the calculator gives you an answer of 1, then you know it's working in degrees. If it gives you a different answer, then it's probably using different angle units, most often radians, and you'll have to look up how to change the units to degrees. So simply divide the size of the baseline by the tangent of the parallax angle. This will give you an estimate of the distance to the target in the same units you listed the baseline in. The second approach is called the small angle approximation. This is just a way of avoiding using trig functions, but it works best when the angle is small. Just multiply the baseline by the constant 57.29 degrees, and then divide by the parallax. Again, you'll get a distance to the target in whatever units you have the baseline listed in. Compare the results of these two calculations in Table 2 and find the percent difference between the two. This tells you how much of a difference using the small angle approximation makes here. In effect, it's telling you how good of an approximation this is. Next, see if you can find an independent way of measuring the distance to the target. This could mean using a tape measure, a yard or meter stick, or even measuring the length of your stride and then pacing out the distance. The goal here is to determine if parallax does as well as these other methods of measuring distance. In addition to estimating the size of the error in the parallax measurement, this is also a good time to think about whether the small angle approximation was a good approximation in this case or not. If the percent error in the small angle approximation in Table 2 was small compared to the percent error in Table 3, that tells you that the small angle approximation works well here. On the other hand, if the error in the small angle approximation is larger, then you know you need the accuracy of working with the trig function. In this last part of the lab, you should see how far you can use the angle measurer to measure distances. The accuracy of your angle measurement is directly dependent on the size of your baseline, so you'll want to start by making as large a baseline as possible. Feel free to use a tape measure, yardstick, or even pacing off the distance to define a large baseline. How big you can make this will depend on what sort of spaces you've got available to you. Try going out to a park or other open space where you have some room to work. This should let you measure distances to targets that are much farther away. Can you measure a distant tree, light post, or building that is a block or more away from you? Having a more distant target means you'll need to use a reference object that is a lot further away. Remember that the reference object should be at least several times as far away as the target. Again, you may want to use a more distant tree or building as your reference. If you've got a view of the mountains in the background, that can work very well, provided you can pick out a specific point, like a peak, to measure from. Repeat the distance calculation you did before, and remember to show your work. Also, try to estimate the distance to the target using an independent measurement, and compare that with your parallax measurement. You might have to use something like an online map program to get your independent measurement. Finally, think about other ways you can improve the parallax measurement technique. Be as specific as you can about what sort of changes you could make in the lab to make the distance measurements more accurate. Remember to turn in all of your work, including the tables, your answers to the 4 questions, sample calculations, and a labeled sketch and/or photo of your experiment.